Welcome back to another lecture in space robotics. Today I'll cover the communications subsystem, or comms. This is a critical part of any space robotics mission. Without it, we have no way of getting our precious data back to Earth and no way to tell our robot what to do next. It's the vital link that connects our robotic explorer back to the scientists and engineers on the ground. Today, I'll break down the communications subsystem. My goal is for you to understand the communication subsystem's function, typical requirements, design considerations, and verification methods. And we'll also talk about various technologies associated with the communications subsystem. To start, let's define what the communication subsystem does. A link is a communication connection established between 2 points or nodes, such as a ground station and a spacecraft, to transmit and receive data over a defined medium, such as radio frequency or optical signals. First, we have downlink, which is the flow of information from the robot back to ground. This is how we get our return on investment. It includes all the valuable science data like images from a camera or readings from a spectrometer. It also includes engineering telemetry, which is the robot's health and status report, things like battery levels, temperatures, and system diagnostics. The other direction is uplink, sending information from the ground control station to the robot. This is how we operate the mission. The most common uplink data is commands, which can be as simple as turn right or as complex as a full sequence of actions for the robotic arm. We also use the uplink to send software updates to fix bugs or add new capabilities, and in some cases for direct teleoperation. As you can see, for some missions, both links are absolutely essential for success. A fundamental concept in communications is the relationship between frequency and information capacity. Let's look at the image in the top left. These wavy lines represent the carrier wave that we use to send data. Notice that in the same 1 second block of time, the 5 Hz signal has very few wiggles, and I can only encode about 2.5 bits. But if I increase the frequency to 100 Hz, I have many more wiggles in that same second, which allows me to encode far more information. In this case, 50 bits. The core takeaway is that the higher the frequency, this allows for higher information capacity. And from this, you can take away 2 key requirements for your mission: data rate and data volume. Data rate is measured in bits per second, or BPS, and it's the speed of the data transfer. It's often driven by your most demanding science instruments. If you look at the graph on the bottom right, this shows an example of a data rate profile for a probe called Da Vinci entering the atmosphere of Venus, seen on the bottom left in this CONOPS. This mission uses a technique called adaptive data rate, or ADR. During the critical descent phase, the radio doesn't stick to one data rate. Instead, it adjusts the rate based on the signal strength it's getting from the receiver, like an orbiter. The graph shows different potential profiles: high, medium, and low. ADR logic will pick the best possible profile in real time to squeeze out the maximum data rate possible at any given moment while maintaining a stable link with a low error rate. This allows the mission to scale the science data being collected with the data rate that the link can support at that instant. This leads directly to our requirement about data volume, which is the total amount of data transmitted over time. During this Venus probe's descent is the integration of the data rate curve over time, or more simply, it's the total area under the curve. By using ADR to keep the rate as high as possible for as long as possible, we can maximize that area, which in turn maximizes the total science I get back from the mission. For a short-lived event like atmospheric entry, maximizing this volume is absolutely critical. Beyond how fast we can send data, we also have to consider when and from where we can communicate. This brings up requirements related to timing and what we call line of sight. First, let's talk about timing and latency. If you look at the chart on the left, you can see the round-trip light time to various bodies in the solar system. Radio waves travel incredibly fast, but space is vast, so there's a significant time delay. A round-trip signal to Mars can take anywhere from 8 to 40 minutes. This latency makes real-time joystick control impossible. It means we have to operate the robot using carefully planned command sequences, and it drives the need for greater autonomy, as the robot must handle situations on its own during that long communication lag. Second, for communication to work at all, we need a clear line of sight to a ground station. The time period when we have a clear line of sight is called contact time. Contact can be broken by several factors. The most obvious is the planet itself. The Earth must be above the spacecraft's local horizon. The ground station must also be within a minimum distance if the communication power is limited. This image shows a satellite's ground track in red and available ground stations in those bubbles. In this scenario, the satellite can only communicate back to Earth when its ground track crosses into the ground station's reception zone. Other requirements we may want to impose on our mission or space robot pertain to our communications link in the form of a link margin and power for transmission. First, let's define a link margin. We can think of it as how robust our communication link is, and a key metric for this is called signal to noise ratio, or SNR. To visualize SNR, look at the bottom image. It shows how a signal degrades as noise increases. On the far left, a high SNR of 40 decibels gives us a clear image and a distinct signal waveform. As SNR drops to 20 decibels and then 10 decibels, the image gets progressively noisier and the signal becomes harder to distinguish from the noise. At 0 decibels, the signal is completely buried in noise, rendering the image unusable. This clearly demonstrates why a high SNR is critical for clear and reliable data. Now let's consider power requirements for transmission. To send a signal over distance, we must overcome something called free space path loss. The top left image illustrates this. A signal from source S spreads out, and as the distance doubles, the area of the signal covers quadruples. This spreading causes the signal to weaken. The equation here quantifies that phenomenon. Ls is free space path loss, lambda is the wavelength, and r is the distance. It shows that loss increases significantly with distance. To maintain a good SNR and a reliable link, we must transmit with enough power to overcome this loss, especially over long distances. This is critical for high-stakes missions like planetary landings, where communication cannot fail. Past requirements, we can start to talk about design. Let's start at a high level with communication architectures, separated in two categories of direct-to-earth and relay. A direct-to-earth link, as the name implies, is a direct connection from, say, a rover on the surface to a large ground station on Earth, like those in the deep space network. An advantage is that it's direct and doesn't depend on any other spacecraft being in the right place at the right time. But because the range is so vast, the rover needs a powerful transmitter and a large steerable high-gain antenna. This consumes a lot of power and adds mechanical complexity. A relay link is a two-hop system. A rover uses a low-power short-range link to send data to an orbiter flying overhead. The orbiter then uses its large antenna and powerful transmitter to relay that data back to Earth. An advantage of this configuration is that the rover-to-orbiter link is very short-range, allowing for very high data rates with the low power consumption. That's extremely efficient. For example, the Mars exploration rovers Spirit and Opportunity returned over 90% of their data using this relay method. A disadvantage is that you are completely dependent on that relay asset. If the orbiter isn't there, or if it fails, you lose your primary communication path. Once you have defined the high-level communications architecture, you can design communication subsystem components on board a space robot. As you see in both samples of flow block diagrams, many different electronic components work together to convert digital signals to radio frequency for transmission, and then back from RF or radio frequency to digital upon reception. Starting at the signal, first, the transceiver is what generates the signal TX and receives the signal RX, represented by this digital baseband input in the top diagram, and the telemetry input on the bottom diagram. Next, amplifiers are crucial for boosting signal strength. The power amplifier in the top diagram boosts the outgoing signal for long-distance transmission, and then filters are used to remove unwanted frequencies. You see them at various stages in the top diagram, and they also exist down here. Filters are placed before amplification to prevent overdriving circuits with noise. For sharing a single antenna, like in the bottom diagram, a diplexer or duplexer is essential. This component efficiently routes signals, allowing the same antenna to be used for both transmitting and receiving. Finally, the antenna is the critical interface between your spacecraft and ground. In both diagrams, it's the last component for transmit and the first for receive. This is where electrical signals become electromagnetic waves for wireless communication and vice versa. These core components, the transceiver, amplifiers, filters, diplexer, and antenna, all work in concert to form a robust communication subsystem, enabling our space robots to send and receive vital data across vast distances. Here I've described core components, but these are not completely comprehensive of all the components you can use in a communication subsystem. I want to focus in a little bit more on antennas. We'll discuss the critical role of antennas in space robot design using the Mars exploration rovers as our example. The antenna is the component that actually radiates and receives radio waves. There's no one-size-fits-all solution. The choice depends entirely on the mission's needs, and RF engineers classify them by their gain. So from this image of the Mars rover, you can see several antennas. There's the low gain antenna, which is simple and often omnidirectional, meaning it transmits and receives in nearly all directions. This is great for emergencies or when the spacecraft's orientation is unknown, as it requires no precise pointing. However, it offers a very low data rate. Spirit and Opportunity use their low gain antennas for initial contact and as a backup. The high gain antennas, which can be seen over there, typically that's a parabolic dish like the one visible on the rover. It focuses radio energy into a very narrow concentrated beam, much like a spotlight. This allows for very high data rates over vast distances. The trade-off, however, is that it must be pointed with extreme precision. The rover's high gain antenna needs a motorized gimbal to constantly track Earth. While not explicitly labeled for gain, the rover also uses a UHF antenna for communicating with the orbiting spacecraft. Now, how do we choose which antenna to use? The top left diagram shows a radiation pattern, which illustrates how an antenna transmits or receives energy in different directions. This particular pattern, common for a parabolic dish, which can be seen here, demonstrates a highly focused beam. The gain, or dB, on the y-axis shows how efficiently this antenna directs power. For high-gain antennas, we aim for a very narrow, high-gain main lobe to achieve high data rates over long distances, but this requires precise pointing to align with the Earth. Lower-gain antennas would show a much broader, less directional pattern. Finally, some critical subsystem considerations for antennas are that structurally, antennas are almost always on the outside of the robot, as they require a clear line of sight to transmit and receive signals without obstruction. Thermally, especially for high power transmitters, antennas can become quite hot, requiring careful thermal management to protect surrounding components. Orientation-wise, high-gain antennas need more precise pointing toward a relay or ground station, requiring coordination in operations with the guidance, navigation, and control subsystem. After the antenna, the signal typically encounters a diplexer. This top image shows the diplexer's configuration on a satellite, while the bottom center diagram illustrates its function more clearly. The diplexer acts as a traffic cop, efficiently multiplexing and demultiplexing different frequency bands. For example, it allows a single antenna to handle both transmit and receive signals, as seen by the transmitter and receiver blocks connected to it. This is crucial for optimizing space and reducing complexity on a space robot like the Mars rover seen on the left, where every gram counts. Next in the chain, we have amplifiers and filters, which often work in tandem. The small green and purple circuit boards in the middle of the slide give you a glimpse of what some of these components might physically look like. Amplifiers are essential for boosting signal strength. When selecting an amplifier, we consider its bandwidth and gain. This bottom graph shows this relationship, that as you increase the amplification or gain, the usable bandwidth of the amplifier often decreases. Conversely, by adding negative feedback, you can limit the maximum gain but significantly improve the amplifier's frequency response, giving you a wider, flatter bandwidth. This trade-off is critical for ensuring our signals are amplified effectively across their entire frequency range. Filters are used to remove unwanted frequencies. They are crucial for rejecting interference and noise, ensuring only the desired signal passes through to subsequent stages. Finally, all of these processed signals lead to the transceiver, pictured on the top right, either for final transmission or for conversion back into a digital signal for processing by the robot's onboard computers. On the Mars exploration rovers, components like those get integrated into the rover electronics module within the rover. Revealed here, you can see specific communication elements like the X-band diplexer, the UHF transceiver, the UHF diplexers, CXS, or coaxial switches, WGTS, which stands for waveguide transfer switches, SSPAs, or solid-state power amplifiers, and X-band transponders, labeled SDST, right here. After discussing different technologies that you may consider in your subsystem, a question you may have is, how do we evaluate whether those technologies will get the communication link to close? This is the most important question for a communications engineer, and is answered through something called a link budget. A link budget accounts for all of the gains and losses a signal experiences on its journey from the transmitter to the receiver. In this diagram, the transmitting signal is sent to the antenna with some power P. It's amplified by some gain, and then there's a loss in transmission, a loss through free space, a loss at reception before the spacecraft finally receives the signal at power PR. Power gains and losses are described in decibels, or dB, which is in logarithmic scale. Working in logarithmic scale is convenient because the math lets us add and subtract instead of multiplying and dividing huge numbers. We want this received power to be above the noisiness of our surroundings so we can hear the signal above the noise. We can definitively say that a link closes when we calculate the energy per bit to noise power spectral density ratio, or EB over N naught. This equation tells me how strong the signal I care about is, or the energy in each bit, is compared to the background noise, which is represented by N naught. For a given modulation and coding scheme, you need a certain minimum EB over N naught to close the link successfully. Let's walk through all of these terms. You start with your transmitter power, PT, and add a focusing gain from your transmit antenna, GT. Then you start subtracting all of the losses. There are losses in the spacecraft's own wiring called line losses. The biggest loss by far is something called free space loss, LS, which is determined by range and frequency. You might also have atmospheric loss as the signal passes through Earth or another planet's atmosphere, represented by LA. On the plus side, you have the gain of your receive antenna, GR. Finally, we'll account for the noise in the system. Noise is a function of the system's temperature, so in this ratio, I divide the system noise temperature TS and the Boltzmann constant K. Crucially, you also subtract, or in this case divide, the data rate RB. Notice that the data rate is treated as a loss here. This shows a fundamental trade-off. For the same system, if you want to increase your data rate, your EB over N naught will go down. Your job as an engineer is to design a system where, after all this math, the final EB over N naught is greater than what's required for a reliable link. That positive difference is called your link margin, and a healthy margin is key to robust design. Now that we've introduced all the key contributors to the link equation, let's take a step back and ask, is our signal stronger than the noise floor? That's really at the heart of a link budget. The goal is to ensure that the energy per bit, EB, is sufficiently higher than the noise power spectral density N naught. This is what that ratio quantifies. And this diagram gives us a visual intuition for what EB over N naught really means. Just like in those images, imagine your receiver picking up a waveform like this. The yellow trace represents the incoming signal. Most of the time, it's just fluctuating around some baseline. That's the noise floor, the ever-present background noise in your system. But occasionally, we see strong peaks that rise well above that floor. These are the bits we're trying to send. EB over N naught is a way of quantifying how distinguishable these peaks are from the noise. It tells us, are the bits we care about actually visible above the random fluctuations of noise? And if the signal sits clearly above the noise, like in this plot, then EB over N naught is high, and our receiver can confidently detect and decode that data. But if those peaks start getting lost in the noise, the link won't close. Errors go up. Communication breaks down. When we're designing a communications link, some parameters are just fixed. We can't do much about the distance or the space environment, but there are design decisions we can control, especially when it comes to gains. Let's start with transmitter power. This is the raw energy we choose to put into the signal. It's a trade-off. More power improves the link, but it also costs more energy from the spacecraft to operate, say, science. Then there's the transmit gain antenna, GT. That's what the diagram on the left shows. Higher gain antennas, like the 15 decibel one, focuses energy into a narrower beam. That means more signal strength in the direction we care about and a stronger link over long distances. But narrow beams also require better pointing accuracy. Low gain antennas, like 3 or 9 decibels, are more forgiving, but less efficient at getting power to the receiver. And finally, we also have control over the receiver gain antenna, GR. This tells us how well the receiver collects energy from incoming signals. Bigger dishes or more sensitive antennas can pull in more signal and help us detect weak transmissions from far away. So the 3 questions on this slide are all about what we can choose. How much power should we transmit? How big and focused is our transmit antenna? And how sensitive is our receiver? These are the knobs that we can turn, the gains that shape the strength of our link. So far, we've talked about the parts of the link we can boost, things like power and antenna gain. Now let's shift to the other side of the equation, losses. There are things that weaken our signal before it even reaches the receiver. Let's start with the biggest one, free space path loss, or LS. This is the signal strength we lose just by spreading energy over distance. It grows with the square of range. So the farther away your spacecraft is, the weaker the received signal is. There's another type of loss we need to consider, and that's where this plot comes in. This diagram shows atmospheric opacity, or how transparent Earth's atmosphere is to different wavelengths. You can see that certain frequency, especially in the infrared and the ultraviolet, are completely blocked. That's your transmission path loss, or LA. Even if you design a perfect link, if you're transmitting at a frequency that gets absorbed by the atmosphere, your signal won't make it through. So part of your job is to choose a radio frequency that sits in a clear window where the atmosphere is mostly transparent. Finally, we have to think about noise. Noise comes from the system itself, from electronics, from the receiver, and is related to the temperature, or system noise temperature. Higher temperatures mean more thermal noise in your signal chain, and that noise is multiplied by Boltzmann's constant, K, to give us N naught, the noise power spectral density. The last question we can ask in design is, what temperature are we operating at, and can we cool the system to reduce noise? Now it's time to put all of those pieces together. This next activity walks you through the process of building a link budget and understanding how every design decision affects overall system performance. The spreadsheet shown here was originally created by Jan King of AMSAT or IRU, and it's an incredibly helpful tool we'll use in this course. It organizes all of the gains and losses and noise sources we've been talking about and helps you track them from first principles all the way to mission level performance. So take a look at the top left diagram. This shows the flow of power through the system from the transmitter through antennas in the link into the receiver. Again, we accumulate gains and losses, pick up noise from multiple sources. That same logic in the flow diagram is formalized in this spreadsheet on the right. The spreadsheet has many intermediate tabs like a layered calculator. It starts with detailed design parameters like frequency, power, antenna size, and temperature, and then feeds them through nested spreadsheets that calculate intermediate values like EB over N naught or S over N, and then ultimately the link margin. The goal is to end up with a clear system performance summary, the sheet that I am showing you here, both for your uplink and your downlink. And with that summary, you'll be able to definitively say whether your link closes or not. This activity is your chance to explore the trade-offs. How does changing power or antenna gain affect performance? What happens when you increase data rate? How much margin is left? By filling out this spreadsheet, you'll learn how to reason about a communication system like a mission designer. Let's finish our tour of the System Performance Summary tab by focusing on one of the most important outcomes, the link margin. Over here. This is where we bring everything together, power, gain, loss, noise, and data rate, to ask one final question of, is our signal strong enough to close the link reliably? The metric we use is EB over N naught. You can see that the value calculated on the left side of this summary, here it's about 22.8 decibels, which tells us how far above the noise floor our received signal is. But just being above the noise floor isn't enough. We also have to compare it to the minimum EB over N naught required by our modulation and coding scheme. And that's where link margin comes in. Link margin is the difference between what we've got and what we need. It tells us how much buffer we have to account for real-world conditions like antenna pointing errors, weather effects, especially for Earth-based links, and our components aging over time. The general rule of thumb is a 3 decibel margin, which means you have twice the power you minimally need. A 6 decibel margin is common for critical links where reliability is non-negotiable. On the right side of the slide, you can see 2 margin outputs, one for EB over N naught and one for S over N. In both cases, the link margin is well above 0, so the spreadsheet tells us confidently, the link closes. That's great. This is the final checkpoint. If your link margin is negative, or even just razor thin, it's time to revisit the design. To help you use the spreadsheet, I'll talk about all the different tabs that are in the spreadsheet. Each tab represents a different piece of the communication system, and many of them feed into one another to calculate your final link budget. Here's a quick overview. The title page provides a basic overview of the spreadsheet, like what version it is, credits to authors, and a place to document your mission. IIRR stands for Introduction, Instructions for Use, References, and Revisions. That talks about how to use this spreadsheet, where to put your user input, and we'll go into that in the next slide a little bit more deeply. Orbit is a tab where you define your spacecraft's orbit, and this could be your planet's orbit. You can choose between low Earth orbit, high Earth orbit, geostationary, or deep space, or you could even customize for a certain celestial body. You can then enter parameters like altitude, inclination, and elevation angle. You'll notice that those blue cells are your inputs, and those are the cells that you can edit. In this example, we are using a low Earth orbit with a slant range of about 1,440 kilometers. That geometry then feeds into path loss calculations later on. Frequency is where you select your operating frequency for both uplink and downlink, a key choice that affects atmospheric losses and antenna design. The transmitters and receivers tabs define the electrical characteristics of your radios, like output power, internal noise figures, and power consumption. The antenna gain tab calculates how focused your antennas are based on parameters like dish size and frequency. The antenna pointing losses model how much signal is lost due to imperfect pointing or spacecraft jitter. The antenna polarization loss covers mismatch losses between transmit and receive polarizations. The atmospheric and ionospheric losses calculate absorption, scintillation, and other frequency-dependent effects. The modulation and demodulation method tab lets you define how your signal is encoded and what EB/N0 threshold is required for your chosen modulation scheme. The uplink and downlink budget tabs are at the heart of this spreadsheet. They pull in data from all the previous tabs to calculate gains, losses, noise, and finally link margin. The system performance summary rolls everything up as you saw in the last slide, and you can quickly check when your link closes, and if not, then a signal for redesign. In this slide, you saw the orbit tab to give you a sense of how user inputs are structured. Your job is to enter in all of those blue cells and let the spreadsheet do the rest. At this point, you've seen how the spreadsheet is structured and how each tab feeds into the final performance. Let's talk about how you can help yourself as you start working through the spreadsheet. There's an excellent walkthrough video created by Jan King, the original designer of this tool. It's called Link Budget Walkthrough, and you'll find it linked right at the top of the IIRR tab in the spreadsheet template. IIRR stands for Introduction, Instructions for Use, References, and Revisions. And this is a great starting point. It includes color coding explanations, how-to notes, and guidances on how to use the spreadsheet without breaking key references between sheets. Most importantly, don't worry if you don't have every input nailed down right away. At the beginning of space system design, that's completely normal. Just input something reasonable to get started, even if it's rough, and flag it for refinement later. Design is an iterative process. You'll circle back to this spreadsheet again and again as you define your spacecraft, your mission concept, and your constraints. The real goal of this activity isn't to generate a perfect link budget right away, it's to understand how design parameters affect performance and to give you a tool you can rely on as your system evolves. Once your link budget is defined and it works on paper, the next step is verification. We make our move from modeling to testing to make sure the system performs in the real world, with all its messiness and surprises. Let's start with the most intuitive test, range test. This answers the question of how far can your radio actually communicate. The general idea is that you transmit from one end and then you receive on the other end, across distance, terrain, or even orbit. This validates the assumptions you made in your link budget. Next, we have something called RF spectrum analysis. This lets you see if your signal is in the frequency domain that you expected. You check for interference, spectrum crowding, and whether you're staying within your assigned band. For more work, there's also antenna radiation pattern testing, usually done in an anechoic chamber like the one shown here. This is where you map the actual beam shape, gain, side lobes, and polarization that we saw in a previous slide to ensure the antenna behaves as expected. And behind just this subset of testing are other tests that support system verification, like loopback and end-to-end testing to confirm the whole signal path works, protocol testing to make sure packets are well formed and timing is correct, and eventually environmental testing like thermal vacuum or vibration to simulate launch in space conditions and see if your comm system holds up. The core idea of testing is to analyze it, simulate it, and then test it rigorously so your communication subsystem is ready for flight. I hope that by the end of this lecture and your readings and activities, you're able to define the function, typical requirements, design considerations, and verification methods for communication subsystems. I also hope that you're able to identify and select different technologies for your communication subsystem design. See you soon.